Okay, and for this last video in sections 12.7 and 12.8, we're going to look at problem number 6. It says, consider an object moving in the plane subject only to the force of gravity. Newton's second law then implies that the acceleration of the object is constant and is equal to negative g times the standard basis vector j, where here g is known as the constant of gravitation, and it's approximately equal to 9.81 meters per second squared. Okay, so we have this object moving in the plane. The only force acting on it is the force due to gravity, and so as a consequence of Newton's second law, this implies that at every point along our path, the acceleration vector points directly down in the direction of negative j, and its magnitude is equal to the constant of gravitation, right, which is about 9.81 meters per second squared, right? That's this number g. Okay, so for part A, it says let v sub 0 denote the object's velocity at time t equals 0. Derive an equation for the velocity of the object at time t. Well, we know that the acceleration is the derivative of the velocity. Okay, so put another way, the velocity is an antiderivative of the acceleration, so we'll go ahead and integrate. And so this will give us negative gt times the basis vector j plus a constant of integration, and here since we're integrating a vector function, our constant of integration is in fact a constant vector, and I'll call that c1. And since we're calling our velocity at time t equals 0 v sub 0, note that if I plug in 0 for t, I get that this constant of integration c1 is equal to v sub 0. And so putting that all together, our velocity at time t is equal to our initial velocity v sub 0 minus gt times the basis vector j. Okay, cool. Part B, pretty similar. It says let r sub 0 denote the object's position at time t equals 0. Derive an equation for the position of the object at time t. Okay, so we're going to go ahead and integrate again, right, since the velocity is the derivative of the position, right? So position is an antiderivative of the velocity. So this gives us v0 times t minus 1/2 gt squared times the basis vector j plus another constant of integration. I'll call that c2. Okay, and now since we're calling our initial position r sub 0, right, if you plug in 0 for t, these first two terms just drop out, and you find that this constant c2 is equal to our initial position r sub 0. So you put that all together and you get the position r at time t is equal to the initial position r sub 0 plus the initial velocity v sub 0 times t minus 1/2 gt squared times the basis vector j. Okay, great. And so now for part C, it says assume that the object is launched from the origin at an angle alpha, where here alpha can be anything from 0 to pi over 2 inclusive, above the horizontal with an initial speed, which is just the magnitude of our initial velocity v sub 0. Derive an equation for the position of the object at time t. And then it says your answer should depend on g, alpha, and the initial speed. Alright, so I'm going to make a little space here. So we're just going to make use of our result that we just derived here in part B. Okay, now in this scenario, right, we're launching this object from the origin, so our initial position r sub 0 is the 0 vector, and we're launching this object, right, at an angle of alpha with the horizontal. Okay, so if I want to write out the initial velocity vector in component form, okay, just making reference to this right triangle here, the I component is just the magnitude times the cosine of this angle alpha. So in other words, it's the magnitude of the initial velocity vector times the cosine of alpha. The j component likewise is the magnitude of our initial velocity vector times the sine of alpha. Okay, so there's the initial velocity vector in component form. Okay, and so applying the results from part B to this scenario, right, we're going to get that r of t is the initial position, which is the 0 vector, plus the initial velocity vector v sub 0, which I have right here in component form, times t minus 1/2 gt squared times the basis vector j. So now if I write this all out in component form, okay, multiplying v sub 0 by t, that's just going to multiply each one of these components by t. So we get, right, our initial speed times the cosine of alpha times t for the I component of v0t, and then we're going to get the initial speed times the sine of alpha times t for the j component of v sub 0 times t, and then we still have our minus 1/2 gt squared times the basis vector j. Now if you combine j components, we get this expression for our position at any time t. Okay, great. So now let's go ahead and press on to part D. It says, find the time of flight of the object, which is the total amount of time the object is in the air. So we're launching the object from the origin, so what we really want, right, is the time when the object will land, right? That'll be the total amount of time the object's in the air, and I'll call that time capital T. And this will occur, right, when the object lands and there y is equal to 0, right? So I'm just going to set the j component of our position vector r of t equal to 0. And notice there's a factor of t in each one of these terms, so I'll factor that out. And so I get two solutions. T is equal to 0, and from this other factor, 2 times the initial speed times the sine of alpha over g. Now when t is 0, right, that's just when we're launching the object. Okay, so we want this other solution, and so we conclude that the time of flight there is twice the initial speed times the sine of alpha over the gravitational constant g. All right, and then for part E it says, find the range of the object, which is the horizontal distance the object travels. All right, well that's just going to be the x-coordinate, right, at the point where the object lands. And so what I want to do there is just plug in, right, the time of flight, capital T, into the I component coming from our position vector. Okay, so this is going to be our initial speed times the cosine of alpha times the time, and that's just this expression for capital T. So notice here I get the initial speed squared, and then I have this division by g there, and then I have 2 sine alpha cosine alpha. And I just note here from the double angle identity for sine, that's sine of 2 alpha. So I get this expression for the range of the object, which again is just the horizontal distance the object travels. Okay, great. So now let's go ahead and apply all of these results to part F. And this says a golf ball is driven down a horizontal fairway with initial speed of 60 meters per second at an initial angle of 30 degrees above the horizontal from a tee with negligible height. So again, we're just assuming we're launching it from the origin. Neglect all forces except gravity and assume that the ball's trajectory lies in a plane. Write an equation for the position of the golf ball at time t, and then find the time of flight in the range of the ball. When is the speed of the ball a maximum, and when is it a minimum? Okay, so here's our result from part C, and here our initial speed is 60 meters per second, and our launch angle alpha is 30 degrees. So if I go ahead and just plug those values in, well, I get 60 times the cosine of 30 degrees. Cosine of 30 is root 3 over 2, so 60 times root 3 over 2, that's 30 root 3, and then I have the times t, and so that's my I component. For the j component, well, I have 60 times the sine of 30, and the sine of 30 is a half, so 60 times that is just 30, so I get 30t minus, and then half of g is 4.905, so I get 4.905 t squared there, and then those together make up the j component. Okay, cool. So that's the position at time t. So then how about the time of flight? Well, just plug these values in for our initial speed and alpha into the expression we derived just a moment ago for the time of flight. So that's twice the initial speed times the sine of alpha. So that's 60, right? Because it's 2 times 60 times a half, right? So that's going to come out to be 60, and then we're dividing by g, which is 9.81. So that's about 6.116 seconds. That's the amount of time the ball will be in the air. And then for the range, we just plug those values in for the expression for the range. So we want to take the square of our initial speed, so 60 squared divided by g, and then I'm going to multiply by the sine of twice alpha. Well, that's going to be the sine of 60 degrees, right? Because I'm doubling 30 degrees, and so the sine of 60 is root 3 over 2. So you multiply those together, and you get about 317.807 meters, right? That's the total horizontal distance that the object, in this case the golf ball, will travel. All right, great. And then for this last part about the speed of the ball. Well, what's the speed? Well, the velocity, I just differentiate the position vector component-wise. I get 30 root 3I plus 30 minus 9.81 tj. So then the speed, that's just going to be the square root of the sum of the squares of the components. So square of the I component, you get 2700 plus the square of the j component. Okay, and I want to know, when is this thing going to be a maximum and when is it going to be a minimum? Well, this square root term will be a maximum when the quantity inside the square root is a maximum. And that's easier to analyze because it's actually just a quadratic function in t. And likewise, the square root term will be a minimum when the quantity inside the square root is a minimum. So the idea here is just to look at that quantity inside the square root, and it's just a nice quadratic, okay, and its vertex occurs at half of the time of flight. So it's about 3.058 seconds, okay, and the value at 0, right, when we launch the ball, and the time at impact, right, when the ball will land, that's when we're at the time of flight, right, that quantity has the same output value, right? So we see here we have a max speed at 0 and at about 6.116 seconds. So in other words, the speed is a maximum right when the ball is hit and then when it lands. And the speed is a minimum, right, at half of that range, and that's right when the ball reaches its maximum height above ground. Okay, great. Well, that's going to do it for this question and for these two sections. Thanks so much.